Okay, Michael, thank you very much. And it's a pleasure to be here, or let's say virtually, but I would like to thank you and all the organizers who gave me the opportunity to give this talk. So just please pay attention that sometimes I sort of did something wrong. And also sometimes I see that my name appears as Shmuel Friedland as my Google email address. Second one, I don't know why, but now I hopefully fix. So David, can we please go to the next slide? Okay, here. Okay, so first of all, sort of like a word of wisdom. So matrices are natural and have many remarkable properties that many people already discussed here. And because in many instances, they represent linear operators. And so tensors are hard, and many natural properties are NP-hard. So why? Because tensors are closely related to system of polynomial equations, like we already saw that in the talk of Christian Ickenmeyer. So in this talk, I'll try to discuss the complexity of computation of tensor rank over C or any algebraic closed field, and best rank one approximation of real complex symmetric tensors. The reason I'm sticking mostly to symmetric tensors because it's easier to explain the ideas. David, please, next slide. Okay, so let's do some notations. I mean, I cannot do it, David does for me. So on the first line, you see standard notation. The square sort of n is a set of integers from 1 to n. Bold n is a vector with integers, positive integers coordinates, and bold n square is just a product of all these n's, which I'm not sure I'm using. So for most of the time, F is complex field, C or R, and the tensor product of D vector space. So it's denoted like that, tensor D, F, and then J. And the mod tensor T or script T, it has coordinates Ti1 up to Tid. And each ij is in nj, and we have d modes. So d equals 1 is a vector, which usually I treated as a column vector, d equals 2 as a matrix, and d greater or equals than 3 as tensor. So rank 1 tensor is just outer product of d vectors, each of them different from 0. So if I want to take the inner product over complex numbers, is sort of like bracket TS, so you need to take a conjugate. So it's Ti1 up to Tid and Si1 up to Id. Then the Hilbert-Schmidt norm is the square root of the T product with itself. Now, I will usually use a contraction. I have a tensor T D mode, and I have a, let's say, a product of D minus 1 vectors. And then we contract it. So we, on the last T minus 1 indices of T, and it's going to be a vector Fn1. So we also want to contract on all the indices. So this is T with x1 up to xd. Now, the reason I do that and not use inner product because I don't have the bar. And sometimes I will use S and F to stand for the unit sphere in Fn. David, please, next slide. Now, let's, for simplicity, consider equidimensional tensors. So it's a product of D of Cn, and we assume that D greater or equal to 3. So what is the rank of T? Well, it's a minimal decomposition of T as a sum of rank 1 matrices. And we already know that it's NP-hard, this is Huston. So, but okay, so NP-hard, but suppose I want to find what is the rank. So what is the complexity of the computation? What can we do? Okay, it's hard, but hey, what we maybe want to do it. So there is a very simple way that we found, and this is what I'm explaining now, is a joint work with my former student, Mohsen Aliabadi. So suppose that rank tau is greater than R. So what does it mean? Well, I take the rank, I'm not sure if you can see, I can see it, okay. I take the sum of the, let's say, of R rank 1 tensors, which are with coordinates unknown. It can, okay, minus tau, and this is equal 0. So this is sort of a system of equations in in all these variables, and the number of equations is n to the power d as the number of coordinates in T. So the number of variables are dn because each product, the tensor of rank 1 is dn, and you have r of them. And the number of equations is nd. So this over the algebraically closed field like C, this is the system 1 is not solvable if and only if we have Hilbert-Nullstellensatz ansatz, which means that there are polynomials, so that gi 1 up to id, that I multiply them by the corresponding coordinates of in 1, and this is sums to 1. David, please. Okay, so let's do that for subsets of symmetric tensors. So for that, we slightly want to be, not to talk about the rank, but symmetric rank. So it's a minimal R such that I present S as the sum of rank 1 symmetric tensors. So S rank of S is greater or equal than rank of S, and strictly inequality may hold. This was proved by Shitov. So what does it mean that S of rank of S greater than R? If this system, which is I call number 3, which is sum of, let's say, sum of R of rank 1 symmetric tensor minus S is not solvable. So now what is the number of variables? Now the number of variables here is Rn. What is the number of equations? Well, the number of equations is essentially the dimension of symmetric tensors, and it is equal. So, but in symmetric tensors, we can arrange the indices in the, if you look at the bottom, in the non-decreasing order. So it is a dimension of homogeneous polynomials of degree d with n variables, which is n plus d minus 1, choose d. So Hilbert-Nullstellensatz here is the same as before. You have gi1 up to gid, x1 up to xr, and times the right-hand side of 3, and its sum to equals to 1. And I1 up to ID, they are non-increasing. Okay, David, please go next. We'll go to the next slide. So now, so the whole point is actually efficient version of the Hilbert-Nullstellensatz, which is sort of, there are many variations, but I think I took one which is done by Kohler. So let's assume that the number of variables R times n is less than the dimension of the ambient space of the symmetric tensors. So this actually means that R is at most the generic rank. So you are at line number 3 when you see the, let's say, the blue the blue letters. Okay, so then the degree of each gi1 up to g is at most d to the power, the number of, yes, you can maybe line number 4 if you can put it, David, line number 4, but it's, I don't know, okay? It's d to the power, the number of variables minus 1. So now, how many linear equations we have? Well, it is a dimension. So I'm now at equation number 3 or line number 5. So we have Rn plus delta, choose delta linear equations, right? And we have, and the number of variables, it's as the number of polynomials times the coefficients in each polynomial. So in other words, I may be omitted here. I expand each polynomial gi1 up to id in terms of its coefficients times the monomials. Okay, so its upper estimate, you says the number of variables is n to the power d polynomial, but you have d to the power rn minus 1 times rn variables, and this is d to the power rn minus rn equation. So if I do just Gauss elimination, because it's all linear equation, it's you see that I'm on line number 3 from the bottom. It's the complexity of lobes is O of d to the power 3 rn minus 1 rn. Okay, so now Can we have some lower bounds? That's, of course, we don't know, but my intuition or suggestion is follows, that we know that if R is less than R generic, then a generic tensor of rank R has unique decomposition. But in this unique decomposition, it's because the polynomial approach, we sort of can shift the order of the decomposition. And this gives me R factorial, which is R when R big is like R to the power R. And so this is the upper bound on sort of, I think, the lower bound for R factorial for this decomposition, but I don't have a proof for this. You know, this is the intuition. So I mean, this is sort of how I think at least how much do you need? Okay, the next slide, please.
So there was a question by Eddie now.
Sure.
Maybe
okay. So sure. Let me just look at the question.
Oh yeah. Okay. Wait.
I think that if you look at his paper, Collery says that they're sharp. You know, so he has examples. Collar has examples that his bounds are sharp in certain instances. Okay.
Yeah. So, but do you know that for the tensor decomposition?
No, no. Of course, I don't know. That is a question. No, that would be a good one. No, that's I don't know. I just pulled off the shelf what is available. That is a very good question, and I don't know the result. And maybe there is a place to improve. Okay. Okay. So how do we do rank algorithm? Okay. So first of all, we're trying to find if the S rank of S is 1, which is the same as the rank of S is 1. That is very easy. So you just sort of unfold in one mode and see if the corresponding matrix is rank 1. Okay, but suppose it's not. So now let's do the steps. Suppose that S rank of S is greater than K. Okay, then what do you do? So you check if the system 2 is solvable for R equals K plus 1. If it's solvable, it means the rank of S rank of S is greater than K plus 1, then you repeat to 2. Otherwise, S rank S of K plus 1 and you're done. So flop complexity is essentially, it should be the d to the power 3 S rank S times dn minus 1 times S rank S dn. Well, you will say, hey, this is terrible, but it's only exponential, because if you do the, let's say, classical elimination method for solving polynomial equation is doubly exponential. So it's not as bad as it looks. Okay, David, please, next slide. Okay. So you can do, okay, you can do slightly, first of all, a proof. First of all, you can assume that S is concise in the language of J.M. Landsberg. And so then R is greater or equal than N. And now you can also do it, let's say, without assuming that the field is algebraically closed. You can do the same procedure, but what you obtain with this algorithm, it is the rank in algebraic closure, but you don't have to go to algebraic closure. Okay, so you can try to say field of real rational, Gaussian rational, finite field, because once you have a finite field or you have over integers, there's some random processes that using finite field, and then here I think also there can be improvement. Okay, so no more questions. So let's continue to the next slide, please, David. Okay, so now we are going to the spectral norm of tensors. So here, here I want to convince you that this way of polynomial equation actually gives some new result, that you know that essentially if we fix the dimension n, and let's say we talk about only qubits, and now therefore, so we only want to change d. So then we claim that essentially the spectral norm of tensors is polynomially computable in D. It's not true, it's n. It's no, for n is no, it's np hat. Okay, so let's do now a little bit more specific. So now let's assume that we're in general case, the tau is, or t is just a general tensor. So what is a spectral norm? So you sort of try to contract T with a rank 1 tensor where each x is of norm 1 and take maximum of that. And of course, this norm is less equal to the Hilbert-Schmidt norm because in Hilbert-Schmidt norm, you hit the contract with respect any tensor S of norm 1. Of Hilbert-Schmidt norm. Okay, so for tensors, we know that there is a difference if you take x to if t is real, but if we can take x real or complex, it's not the same, so it can be increased. In other words, if I take a real tensor and look at the spectral norm over reals, it can be strictly less than the spectral norm over complex. Okay. However, if the entries are non-negative, then it's not true, then it's the same, and you just, because you can choose x actually to be non-negative. Okay, so now we are going to go to the symmetric tensors. There's a spectacular Banach theorem in 1938 that it says that in order to find the norm, the spectral norm of symmetric tensor, it's enough to contract with a rank 1 symmetric tensor. Well, this is very nice result, and the proof is also very nice. You should be able to look at that if you can read German. It's a simple German. Okay, so because this result is so important, it was rediscovered many times, but we should give the credit to Banach. Okay, David, can you go to the next slide, please? Okay, so now we all know, or most of the people know, that symmetric tensors is just another way of homogeneous polynomial. So we look of fx as a homogeneous polynomial of degree d in n variables. So we write it in terms of coefficients. When the monomial is x1j1 up to xnjn, the first line. Now here, it be not clear. Somebody sees the first time. It's better to scale the coefficients of f j1 up to ja with something multimonomial coefficient. We'll explain later. So we can do second line fx is cj fjx, and x to the power j is just the monomial, and cj is the multinomial coefficient. And jdn is just the sum of all indices j, which j's are non-negative integers, sum of d. So the dimension of homogeneous polynomials is n plus of degree d with n variables, and n plus d minus 1, choose d. And if you do the standard identity for these coefficients, then it's also n plus d minus 1. Choose n minus 1. So for example, if you want to talk about qubits when n equals 2, the dimension is d plus 1. Now, if you fix n, that's what I want, and you vary d, then the dimension of PD and F is just something, it's d to the power n minus 1 divided, I think, like n minus 1 factorial, something like that. Okay, so we can sort of define an inner product of two polynomials or polynomial coefficients, and you have to be careful. You see, it's weighted, and then we can define the Hilbert-Schmidt of this f of the bold f. Now we also can define the spectral norm of bold f, and this is just, it has very simple geometrical meaning. It's just maximum of absolute value of x on the unit sphere. David, please, next one. Okay, so what is the connection to symmetric tensors? So if we take symmetric tensor and contract it with x to the power d, then we are going to get fx. And so this is, so in the second line, you see this summation. So there is a way, so essentially, fj1 up to jn is equals some entry of the symmetric tensor. How? I take Si1 up to ID, and if I have L index L, I count how many times L appears in this I1 ID, and this is going to be JL. Okay, so then the Hilbert-Schmidt norm of F is the same as Hilbert norm of S, and the spectral norm of S is the same as spectral norm of F. So we have trivial estimate that the spectral norm of F is less equal than the Hilbert-Schmidt norm. So here's one of my recent results on arXiv that I think maybe put last month or maybe this month, is that suppose I take F to the power K, just take a polynomial and multiply K times, okay? And then I take its Hilbert-Schmidt norm, so Hilbert-Schmidt norm of coefficients, and I take its 1 over K. This converges to the limit because essentially log of that is what we call sub-additive sequence. And essentially this rho 1 of F is an upper bound for the spectral norm of F. Okay, so here you have to, yes, this is, and if you take, if you have a computer, if you take F and you take several to the power K, and so then it's of course the polynomial gets bigger and bigger, and you have more computation, and you take its Hilbert-Schmidt norm, take 1 over K, you have an upper bound for F. Now, if F is unitary diagonalizable, which means that there is unitary U such that Fu of X is sum of powers of Xi to the power D with lambda I, then essentially the rho 1 of F is equals this spectral norm, which is of course in this is maximum of absolute value of lambda I. So for quadratic, we know that rho 1 of F is exactly F sigma of F or spectral norm. So what happens for D greater equals 3? What is the, let's say, dynamic interpretation of that? Okay, David, next slide, please. So how much time do I have? I think I have 7 minutes. Okay, so now let's go to measure of entanglement, because as Alessandra says that this is one of the ways we want to measure the entanglement. So a state in physics is a vector of length 1, and d-partite state is a tensor, d-mod tensor, and it's Hilbert-Schmidt norm is 1. So if it's a product state, then it's untangled. Otherwise, it's called entangled, and then this means that it's the spectral norm over C is less than 1. So if we denote by pi n the set of product states, then the geometric measure of entanglement in physics is just the distance of tau to this variety, Segre variety. And so what we showed with Li Wang that the geometric measure of entanglement of symmetric tensor is polynomial compute on D for fixed n, which is equivalent to say that I can compute the spectral norm of tau of symmetric tau for a fixed n with D in the polynomial time. So let's see how we do it. David, please, next slide. Okay, so let's assume that is homogeneous, F is homogeneous polynomial from D and F, and F is real or complex, and we take the gradient of F, and we need to, because of Euler's theorem, we normalize by 1 over D. So we say that F is non-singular as a non-singular hypersurface in corresponding in, let's say, in projective space n-1, if and only if Fx equals 0, the system polynomial equation has only one solution, x equals 0, and x equals 0 is not in projective space. So now, if I want to find what are, let's say, what is the what is the spectral norm of F of corresponding S, I need to look at the the critical points or critical points of fx or real fx, because we are doing over complex, if you want to do it over complex on the unit sphere. Okay, so what the claim is as follows: if we renormalize this critical set, it's equivalent for real case, it's equivalent to the fixed point of fx equals x. Now, in complex case, it is equivalent to anti-fixed points. Now, the problem with algebraic geometry that if you want to look at fx equals x bar, this is not algebraic geometry, and you are in trouble. But then there is a small trick. If I first take fx and iterate that with f bar x, when f bar, I mean I just take each coefficient with bar, then I could absorb the 1c to 2c, which are fixed points of h. So this is, so we can have some price, we add maybe extra fixed point, but we are back in algebraic geometry or in standard solutions of polynomial equation. Now, if f is non-singular, then you have this number of d minus 1 n minus d divided by the 2c projective rays. I think was discovered by Stumpf and his student. And if f is non-singular to C, then for 2C we have this number of projective rays. Now, so what about the real, let's say, anti-bar, let's say, anti-fixed points? Then I know that it's between these two numbers, okay? So now, so what happens if f is singular? If f is singular, this is a zero hyperdeterminant. So it's also, we know a lot. So this lies on a very special very special hypersurface. Okay, so I think I have about 3 minutes, right? Okay, please, David. Okay, so just let me explain a few words. How do we do the computation? So what we do is just we take a Grobner basis, and essentially, if in case of the non-singular, we just sort of find with a projection of this of fixed points on each coordinates, and then after that we have a finite number of points, okay, exponential many, so what, and then we find the maximum, and so this gives us approximation. Now next slide, please. So now, what happens how do I know that if it's non-singular? Well, then I said, okay, then what I'm going to do, I'm going to perturb my f, it's f of t, and take t in some mesh, and then because I know what is the degree of the variety of hyperdeterminant variety, I could do that too. And so again, so what I'm getting is the complexity is, can I have the next slide, please? Then okay, okay, can you back, please? So I'm not sure, can you go, David, can you go back, please? Okay, so here is the complexity. The complexity is essentially of all this algorithm is d to the power n square. Okay, so if, for example, n equals 2, so it would be d to the power 4, right? So, okay, so let's do the next one, and that's the next slide, please. Now, in case of n equals 2, one can do some better, because essentially one can reduce everything to one complex variables. So if you do that, one has much better results. And but I think okay, can we go to the next slide, please? Okay, so next slide, please. So okay, so no, stop, please. So you see, so essentially what we need to find the, let's say, the roots of polynomial equations of degree d minus 1 square, and then to compute. So I think I need to stop here.
Well, I think maybe if you want to wrap it up in a few minutes, I think that's okay. And
okay.
people can already think about their questions
Sure.
for
Okay,
afterwards.
so let's okay, so the point is, okay, David, so let's start going. So there is one extra point that I wanted to tell you. So let's start to do slides next time. Next slide, please. Next. No, before that. Okay, before that. So what the claim is as follows, that essentially you can relate to this, to finding f to some iterations of polynomial maps. And these polynomial maps are essentially you start with the first one. So it says you are looking on tensors which are symmetric in p last coordinates, but not the first one. Now, even if you start with symmetric tensor with m equals n, then when you start to do iterations of maps, is not going to be symmetric. And then you can do, let's say, you can do this limit of fk. Can I get the next slide, please? Okay, so then you can define something like that. So you can define rho 2 of f, which is some limit of the Hilbert-Schmidt norm of fk, and you can define also rho 3 of f, the Hilbert-Schmidt norm, but of something else. And the question is, and you have some estimates. The question is, what is the dynamic meanings of rho 2 and rho 3f? So the last slide I can tell you. Can you go to the next slide, David, please? So the rho 3 of f is essentially related very late in complex dynamic, what's called the Green function. Okay, but rho 2 of f, I don't know. Okay, I think this is the right way to stop.